here we have a source designed to produce X-rays with a wavelength of this guy. What's the unit? What is the energy? And they want it in EV. Normally we calculate energy in joules, but they want it in electron volts for one photon of these X-rays. X-rays. There's two ways of doing this. Way one. I prefer way one, but you might like way two. It effectively involves the same formula. E equals HF. Energy of a photon is equal to HF, which is equal to HC over lambda. The difference between way 1 and way 2 is which Planck's constant you use. I just like using the same Planck's constant all the time. I like using this Planck's constant. So that's Planck's constant. 3 by 10 to the 8 is the speed of light, and the wavelength they give us is 1.4 10 to the minus 10, and that gives 1.42 by 10 to the minus 15 joules. Then we have to turn that, so when you use this Planck's constant in this formula, the 6.63 by 10 to the minus 34, you get the answer in joules. So if you turn that, if you then divide that by 1.6 by 10 to the minus 19, that puts it into electron volts, and you get 7, I think that's 79 electron volts. 879 electron volts. If you do it way 2, you get the same answer, but you use, instead of this Planck's constant here, you use the other Planck's constant on your formula sheet. So E equals HC over lambda equals the other Planck's constant on your formula sheet is 4.14 by 10 to the minus 15. This has different units, that's why it's a different number. Still the speed of light, still the wavelength, and that comes out straight away at the answer, 8879 electron volts. Now the reason I don't like using way 2, I like using way 1, is this, people can get really confused going back and forth between Planck's constants. When do I use one of them, when do I use the other one, and they get a lot of confusion. I just like sticking with the one. I end up using this one more often, I find this one easy to use, and knowing that it always gives me energy in joules and I have to do the transformation into electron volts. If you're happy and you know that using this one is going to give you an answer in electron volts, then by all means use it. If you're happy to go ahead with that and use it like that. But you have to have a really good understanding of why there's two different Planck's constants here, and so understand that they're just really different units and when they can be used, and practice using them in the appropriate place, but just so you don't muck anything up. So what's the momentum of one of these X-rays? Here, this is a way where we could muck it up. The momentum of photons, P of a photon, equals H over lambda. Now for this, you have to use H equals 6.63 by 10 to the minus 34. So if you're going with way 1 and you're always using this Planck's constant, there'd be no confusion here. But if you weren't very skilled, and you just don't know when to use one Planck's constant or the other, and you accidentally put the 4.14 by 10 to the minus 15 in here, you get the wrong answer. So that's why I'm cautious about using it this way. You have to really know when to use it. This can only be used in a case when we're calculating energy. Anyway, what is the wavelength? The wavelength was here. 1.4 by 10 to the minus 10, which gives a very small momentum, 4.74 by 10 to the minus 24 kilograms meters per second squared.